Namaskar and welcome to episode number 5 of Understanding Feynman podcast. Changing electric field produces magnetic field. That's the fourth equation in this book that Feynman has been trying to teach us. And I have a confession. It's not a confession. You should already know this. I'm not a physicist, all right? So this is not you shouldn't study for your exams by listening to this podcast. Definitely not. And this is the first time I'm really confident about what I'm trying to say. This is the first time I understood what I'm trying to say. I think I did understand. Maybe I didn't completely, of course, but I just something turned on in my mind when I read this, which hadn't happened in the whole. Actually, that's not true. Some parts of the chapter were really nice and fine. Let's move on to the actual topic, which is that, okay, this is how do you show that changing electric field produces magnetic field? So this equation has two parts. Okay, this is the fourth equation 1.9 in the book. If you have the book, it says that circulation of B around C can be given by these two terms. First of all, what is circulation of B around C? Okay, in all these scenarios, C is a curve, S is a surface. Okay, so in this case, we are talking about a surface S bounded by the curve C. What does that mean? Make a curve C. In this case, just think of a circle. Okay, think of a circle. Okay, the circle C. And the surface that is bounded by it can be anything that has the circle as its boundary, right? It can be a flat surface, it can be a curved surface. All right. This is the way. Why is this important? Because this is the way to understand the flux and circulation that we already discussed, I think a couple of podcasts ago. And this is the way to do it, by making these imaginary surfaces and these curves and trying to understand how magnetic field and electric field flow through these surfaces and how they are connected to each other and how they change according to each other. So in this case, surface S is bounded by C. Let's say the simplest example would be a coaster, a circular coaster. You know, a coaster, or a disc, or a plate. Okay, or a bowl is not the simplest one, but it's one of them. A bowl, not a bowl. A bowl has this rim which is circular, but has a surface which is curved in 3 dimensions. But it is bounded by that curve in the sense that those are the boundaries of the surface. That curve is the boundary of the surface. Simple terms, right? English. Circulation of B around C. Okay, so if you have a curve C, if you want to find the circulation of B, what is B? B is just the magnetic field, just the term to signify the magnetic field, right? Just go with me here. Don't worry about if you are scared of maths like I am, don't worry. I'm here with you. Hold my hand. Let's go. Circulation of B around C. Very cryptic in that term, but think about each term. Circulation. The magnetic field is circular, right? It's circular around an electric wire. We've already discussed that last time. Remember the lines going through your tension wires that flow from the power station to your homes, they have electric current going through them, and they have a magnetic field which is circulating around it. The farther you are from the wire, the weaker it is, but the closer you are to the wire, the stronger it is, and it's circulating in circles, right? What is the value of that? How do you find the strength of that magnetic field? It depends on two things. This is according to this equation. The first we already discussed, the current flowing through. The higher the current that is flowing through it, the stronger the magnetic field is, right? Right? I think I am making a mistake. Maybe not. Okay, there is a plane going through. Can you hear that plane? I'm sure you can. Listen to that plane. Okay, it's gone. The other, we have already discussed that there is this magnetic field that is created because of flowing current, right? If that were the only thing, there would be a paradox. What is that paradox? Maxwell found out that paradox. Maxwell said that there are these things called capacitors. First of all, if you don't know about capacitors, don't worry. It's a very simple thing. It's not very simple, but it's what I'm going to say is very simple. The simplest capacitor is two plates, not connected to each other, but those two plates are very close distance to each other, but there is some material between them. Don't worry about what the material is. It can also be air, just vacuum and just air or whatever. Can it be a vacuum? I'm not sure. Okay, I'm tripping on my own words. So think of it as air or any electrolyte or whatever. No, cannot be electrolyte. Okay, I'm gonna go ahead. Capacitors are used in circuits all the time, in DC circuits as well as AC circuits, direct current circuits and alternating current circuits. And what the thing with in DC circuits, they are only going to, when they are fully charged, no current will flow through them, right? If it's direct current, right? No current usually flows through. Why would any current flow through it anyway? Because they are not connected. There are two plates separated by some non-conductive material. How can a current flow through them? Good question. In the case of direct current, as you pass the current, one plate will gather all the positive charge that will cause the negative charge to gather on the other plate, right? Because of the strength of the electric field. And because that is happening, there is, from the outside it feels like the current is flowing, but only until the plates are completely saturated with charge. They cannot hold any more charge, and at that time the electric field will stop and the current would stop, and there would be the capacitor would be called as charged. It is used in circuits for so that there is there are examples of using it so that there is when if power goes off, there is like an alternate power in the capacitor that will discharge as soon as you take out the batteries that are connected to the capacitor. The capacitor will start discharging if the two plates are connected to through a circuit. It's complex, but the point is, in our case, just think of it. First of all, in case of alternating current, it will never charge because the current is always changing, going from positive to negative, right? So in case of alternating current, that's not true, what I'm saying. But in case of DC current, the direct current, ATM machine, direct current, the uh, b- think of the moment before it has completely charged. Okay, there is still current that can flow through the wire, right? And between the plates there is an electric field, right? Now keep that in mind as I explain the scenario. There is a wire where the current is flowing. The wire goes into a plate, right? There is a gap between two plates, and then there is the next plate, and then there is a wire going from that plate and forward on, right? Think of it, keep that in mind. Now there is a current flowing through, right? So there will be a circulating magnetic field. We already know that. Don't be confused. We already know this. There is, when I say don't be confused, I'm mainly talking to myself. There is a circulating field going through this curve C, that which is a circle. Think of a circle with center as that wire. Okay. The magnetic field is completely defined. The circulating magnetic field is completely defined by the plate, the surface S1. The surface S1 is just a flat surface going through that circle, a circle C, making a flat disk. Okay. Now electric flux, sorry, the current going through that surface is one of the terms of the equation 1.9 which we are discussing. And that current completely defines the magnetic field, right? Right? The current in that wire is proportional to the magnetic field. Got it? Now think of another surface but with the same curve. It is bounded by the same curve, but it's like a bowl or a bowl, right? But the bottom part of the bowl goes between the plates. Okay, keep in mind we are only considering the moment where the capacitor is charging. Okay, it hasn't charged completely. Okay, according to this equation, the electric current flowing through that surface S2 is of course 0, right? The flux of electric current going through that is 0. Why is the flux of electric current going through 0? Going through S2 is 0 because the bottom part of the surface S2 is going between the plates. Okay, if it's going between the plates, then there cannot be a current that flows completely through that surface. It's entering the curve area, the top part of the bowl, but it stops before it goes through the bottom of the bowl, right? So that imaginary surface S2 has a flux of the electric current is 0, but of course changing the location of the imaginary surface from S1 to S2 is not going to change your real magnetic field B, which is circulating around. The magnetic field B has to be the same whether you consider this flat surface S1 or the curved surface, the bowl S2, because the bounding curve is the same, right? The same curve. Think of this beauty here. the same curve can bind a lot of different types of surfaces, and it's up to you to decide what kind of a surface you will be talking about in your scenario. It's up to you. It's imaginary. It's all imaginary. It's a scaffolding to understand the magnetic and electric fields. So in this case, Maxwell chose a bowl and compared it with the disk, and realized in order for the magnetic field to be the same for both surfaces, once you consider the both surfaces, there has to be another term in this equation. That term in this equation is the change of the electric field through the surface S2, or any surface, right? So first of all, there is an electric field going from one plate to the other, and that is the electric field we are talking about. And that electric field going through S2 must create the same effect, the same exact same value of the magnetic field, because of the second term, or the first term, whichever term you decide is the first. It's an addition, so any term can be first. Don't be confused now. So the whole equation is circulation of B around C depends on two factors. The first one is the flux of the electric current through the surface. The second one is the change of flux of electric field through the surface. Okay. The first one is the flux of electric current through the surface. And the second one is the change of flux with time of E through that surface. Both terms are a part of this magnetic field. In case of S1, one of the terms is 0. Which one is 0? The electric field term is 0 because there's no electric field going through it, only an electric current going through it, which is already taken care of. Right. In case of S2, there is no current going through it, but there is a changing electric field. Why is the electric field changing? Because the capacitor is charging. As the capacitor is charging, the electric field is changing. Got it? And this is how Maxwell theoretically figured out that this is the equation. Oh my god, this honking. Are you done, bro? Yeah. This is how he figured out that this is going to be the equation. I hope you got as much pleasure out of this particularly charged class discussion as I did. Thanks for listening. See you tomorrow, or maybe day after tomorrow. Ciao, ciao.